Hello students and welcome to the next lecture of Laplace transform. Till now we have discussed how to calculate Laplace transform of elementary functions along with the properties of Laplace transform, and then we have calculated inverse Laplace transform by means of partial fractions and by means of using its properties. Now next we will be discussing convolution theorem in this lecture, which is again used to calculate inverse Laplace transform. So in this lecture we will be covering convolution theorem, then we will discuss some of its applications, and lastly we will apply Laplace transform to evaluate certain definite integrals. So let's move on to convolution theorem first. Convolution theorem is basically used to calculate inverse Laplace transform, although the questions which we will be doing by this method can be done by earlier methods also. That means we can calculate Laplace transform of these functions by means of partial fractions as well as by means of properties also. But again there are some questions that can be evaluated by using this method only. So particularly, what is the statement of this theorem? This theorem actually gives you two functions fs and gs, and these functions are such that we know their inverse Laplace transform directly. So we have a function fs and we have a function gs, of which inverse transform is given by ft and the Laplace inverse of gs is given by gt. Now, suppose we have the product of this fs and gs. So, we have the product of fs and gs, that means Laplace of ft and Laplace of gt. And I have to find out L inverse of this product, then it is equal to this convolution integral, which is given by integral 0 to t f of u g of t minus u du. Here what is fu? Fu is actually inverse Laplace of fs, which is ft, and in this integral we replace this t by u. Similarly, g of t minus u is simply the inverse Laplace of this function capital G, and in this integral we have replaced t by t minus u. This integral is again represented as f star g, where f and g are your original functions, and this represents convolution of f and g. So this f star g is nothing but it is known as convolution of f and g, and we also know that it is faulting of f and g. So convolution theorem is actually applied to evaluate inverse Laplace transform of such functions which are multiplied together, and again the necessary condition is we must know the inverse Laplace of this fs and we must know the inverse Laplace of this gs. Now we verify this theorem. To verify this, since we know that we do not have any independent formula for this L inverse, so what I do? I shift this L inverse to the right side, and instead of calculating L inverse of this fs and gs, I will be calculating Laplace of this integral. So to evaluate Laplace of this integral, I assume that this function is denoted as a new function phi t. Why is it so? Because you know that this integral we are performing for u, and the limits of u are from 0 to t. So finally, after integration, this integral will give me a function of t. So I assume that this integral is phi of t. And now we will calculate its Laplace transform, and finally we will prove that this Laplace is equals to fs into gs. So we first assume that this integral is equals to phi of t, and now in order to prove the theorem, I have to calculate the Laplace of this phi t. So I calculate Laplace of this function, and we know that formula for ft Laplace is given by integral 0 to infinity e to the power minus of st, ft and dt. So what I have? This is Laplace of phi t, that means this integral. So I evaluate integral 0 to infinity e to the power minus st, then my ft is this one, 0 to t fu g of t minus u du and dt. Now I have two integrals over here, so I can arrange them in the form of a double integral, which gives me this expression, integral 0 to infinity, and these will be the limits of t. Similarly, the second integral will be from u 0 to t, and I have this function. Now since it is a double integral and I cannot simplify it in the given order, since first integral has to be performed for u, and if I integrate it for u, I have fu which is unknown to me, I have g of t minus u which is again unknown to me. So if I follow the integral in the given order, it is actually difficult for me to evaluate this one. So what I do here, I change the order of integration. To change the order of integration, I have to see the limits here. When I look at the limits of t are from 0 to infinity, that means they are constant. When I look at the limits of u, they are from 0 to t. That means they depend on the variable t. Hence, we cannot directly interchange the order. I have to trace the region and then I will be changing the limits accordingly. To change order of integration, I will be constructing this region like this. Firstly, I'll plot the limits of u. So, u varies from this axis gives you the axis u and this axis gives you the axis t. u0 is this line, that is t axis, and u equals to t will be a line inclined at 45 degree. Now again t varies from 0 to infinity. So, this axis is t 0, and since I have t infinity, so my region of integration will be the right side of this line, that is an open region. After that, since limits of u 0 to t have to be integrated first, so this region will be consisting of a vertical strip, because I have to integrate in the order, u will be integrated in first order and then I have to integrate t. So strip will be parallel to u axis. Now, to change its order, the figure remains same, the region of integration remains same, but the orientation of this vertical strip will be converted to horizontal strip. So, what happens if I change the order? I arrive at this figure in which this axis again represents u, this is again t, the limits of this region are same, it is from t equal to u, here you have t equals to infinity, but this vertical strip is converted to this horizontal strip. After that, now since this strip is parallel to t axis, so now my first integral will be for t. So I look at what are the limits of t. Now this strip varies from t equals to u, and since the right hand side of this region is open, I have t is equals to infinity from this side. So limits of t will be from u to infinity. Finally, I look at the limits of u. So u varies from this line, that is t axis. So here I will be having u0, and since the region is not bounded, it is an open region. So again the limits of u will vary from 0 to infinity. So the limits which were from 0 to t and 0 to infinity now are converted to u to infinity and 0 to infinity. So, since we have changed the order of integration, we have easily found out that limits of t will now vary from u to infinity, and this will be my first integral, and similarly the limits of u will be from 0 to infinity, which is my second integral. So, Laplace of phi t can be written as u0 to infinity, which is integrated in the second order, and t is equals to u to infinity, so on. So this is integrated first for t. Now to integrate it for t, I see this function has t, this function depends on u, so it will be a constant quantity, and the next one I have g of t minus u. So to simplify this integral, I replace here t minus u by a new variable v. And when I use this replacement, I get dt is equals to dv. So let's use this substitution here. I get integral u 0 to infinity. We have not changed this one. Now since I have replaced t by t minus u by v, so now the new limits will be v 0 to infinity e to the power minus s. T will be replaced by u plus v. Then I have fu as such. Then again I have g of v, and then dt will be replaced by dv. And again bracket closed, and then I will be having du. Now again simplifying it further, I have u 0 to infinity. This integral contains f of u, which can be taken common because we are integrating it for v. And from this expression again I can take e to the power minus su common, f of u common, and then we will be having v 0 to infinity e to the power minus of sv, g of v and dv, and this put in a bracket, and then we will be having du. Now if you compare this integral with your standard formula of Laplace transform, you must be ensuring that this is e to the power minus st, ft and dt. So this is nothing but Laplace of this function, and hence I can replace it by g of s. Whether I have a variable t or whether I have a variable v, it doesn't matter. So I can write down this integral as u 0 to infinity e to the power minus su, then I have fu, and this complete bracket will be replaced by g of s, and then I have du. Now this integral has to be evaluated for u, so gs will behave like a constant and it can be taken common. So I have this integral as u 0 to infinity e to the power minus su, then fu, then du, and gs taken common. So now again look at this bracket. It is e to the power minus st ft dt, where t is replaced by u. So you can simply see that this is again Laplace of fu or Laplace of ft. So I have the result fs and gs. So this is how we can prove convolution theorem by shifting L inverse to the right side, because we do not know the formula for L inverse, but we know the formula for Laplace. So Laplace of this integral can be shown equal to fs and gs. Now we take some examples which will illustrate more applications of this convolution theorem. We first have this integral. We have to evaluate L inverse of this function. Now, in order to apply convolution theorem, the necessary thing is I have to divide this function in two parts such that both parts can be written in their form of inverse Laplace transform. So looking at this function, you can easily assume that if I take one of the function as this and the other one as this, so I can directly write down their inverse Laplace. This can be converted to cos of some function at, and this can be converted to sine of at. Now the choice of fs and gs is entirely yours. You can take any one of them as fs and any one of them as gs. The order doesn't matter. So again, in order to apply Laplace transform, or in order to apply convolution theorem to this question, what I find, I just separate these in terms of two different functions and I choose one of them as fs and the second one as gs. So let us choose this one, that is 1 upon s square plus a square as fs, and the second one as gs. These two are your standard functions, so you can directly write down their inverse. The inverse of this will be 1 by a sine of at, and again the inverse of this function will be cos of at. Now I know convolution theorem. Convolution theorem gives me L inverse of this function as integral 0 to t f of u g of t minus u du. So what I need to do, I know fs, I know gs, I have calculated ft, I have calculated g of t, so I can easily replace fu and g of t minus u du here in order to get, this is my left side, u0 to t, then I have fu, so it gives me 1 by a sine of au, then again I have cos of a t minus u because I have to replace gt with g of t minus u. Now to evaluate this integral, I have two different trigonometric functions, one is sine and second one is cos. So I have to apply some trigonometric identity to simplify this result. To apply trigonometric identity, you must be knowing that if I have 2 sine A and cos B, if I have this function, then this can be written as sine of A plus B, and we have plus sine of A minus B. So I will be using this result, and since I do not have 2 there, so I multiply the expression by 2 and divide the expression by 2 in order to get 1 by 2a integral 0 to t. Then again I have sine of a minus b, that is au minus at sine of a plus b, so au plus at minus of au, and the second term will be, we have to put a plus sign, then the next term will be sine of a minus b, that is au minus at and plus au, and this completes your integral and it is integrated for du. Now we simplify this one. So I get 1 by 2a integral 0 to t. The first term becomes sine of at and the second term becomes sine of 2au minus at du. We can separate these two integrals. So this will give me 1 by 2a, the first integral 0 to t sine at and du. The second integral 0 to t sine of 2au minus at and du. Now for the first one, I have to integrate it for u and the function is sine at. So it can be taken common from the integral because t is constant for u. So I will be writing it as 1 by 2a. For the first one, I write it as sine at behaves like a constant. The integration of 1 will give me u. Limits will be 0 to t. For the second one, integration of sine will give me cosine of 2au minus at by 2a. And then I have the limits of this integral from 0 to t. Now again substituting the limits, this gives me 1 by 2a, then this gives t sine at. Further, this is minus sign. When I put the limit as t, so I get, this is to the whole. When I put the limit t, this is cos 2at minus at, which is cos at by 2a. So I get cos of at by 2a. When I put the limit 0 for u, this becomes cos of minus at, and cos minus theta is cos theta again. So the next term also becomes cos of at by 2a. Now these two terms are similar, so they cancel out and we are left with only one function, that is t sine at. So result for the inverse of the given function is t sine at by 2a. That means Laplace inverse of s upon s square plus a square can be obtained as t sine at by 2a. These kind of functions, that means if you have s square plus a square to the power n in the denominator, then these kind of functions cannot be solved by any other property. To find out their inverse Laplace transform, we basically apply convolution theorem only, and this is how we can evaluate their inverse Laplace. Now we take one more example for convolution theorem. So again I have to find out L inverse of this given function. To find out L inverse of this function, what I need what is fs and what is gs. So let me write it as fs as 1 by s square and gs as 1 by s plus 1. Now since I have written fs and gs, I need what is ft and what is gt. So we write ft as 1 upon s square. This is again your elementary function, and you have to use inverse Laplace of 1 upon s to the power n plus 1. So I get the result as t here. Similarly, this one is gs 1 upon s plus 1. So I have to use the result of 1 upon s plus a, and I get its inverse as e to the power minus of t. Now, by convolution theorem, I write down inverse of this function, and this will be integral 0 to t f of u. So f of u will be u, and then I'll write g of t minus u. So in this function, I have to replace t with t minus u. So I get e to the power minus of t minus u and du. Now again, integral for u, so t will be constant. I can take e to the power minus t common from the integral, and I have to evaluate integral 0 to t then u, e to the power u and du. Now this has to be integrated by parts, and obviously by using Eilert theorem, first function will be u and second function will be e to the power u. This will be your first function and this will be your second function. So integrating it by parts, I get the result as e to the power minus t as such. Then I have u, e to the power u minus e to the power u from the limit 0 to t. Now replacing upper and lower limits, again I can write down the result as e to the power minus t. This becomes t e to the power t minus e to the power t, and when I put the limit 0, first term becomes 0, second term minus and lower limit minus becomes plus, and I have the result as 1. Now we can multiply the bracket with e to the power minus t, so I get the result as t, this cancels out, the second term becomes minus of 1 and the last term becomes e to the power minus of t. So this is our inverse Laplace of 1 by s square upon s plus 1. This question does not contain the term s square plus a square, so this can be done by other methods also. For this question, you can apply the method of partial fractions as well, and again you can apply the method for division by s also. And convolution theorem can be applied in this way, and if the question asks you to apply a particular property, then you have no choice, otherwise you can do the question by any of the three methods. Now next we will be evaluating some definite integrals with the help of Laplace transform. We illustrate this method by taking some of the examples. The first one is we have to evaluate this integral. The condition that any integral can be evaluated by Laplace transform is it must be an improper integral. That means it must be having the limits from 0 to infinity, and then the integral should be for any variable t or u. So first thing is we consider what is Laplace of this given function. That means I consider integral 0 to infinity e to the power minus st. This integral, then I write down it as e to the power minus of 2t minus e to the power minus of 6t by t and dt. So you can evaluate any integral by means of Laplace transform if it has the limits from 0 to infinity, and we can introduce some exponential in its integrand or in its kernel. So now again, if you remember the formula for Laplace transform, I can write it as this is integral 0 to infinity e to the power minus st, ft and dt. So this can be written as Laplace of e to the power minus of 2t minus e to the power minus of 6t by t, right? Again, if you compare these two integrals are exactly same if I remove this term. And how this term can be removed? If I put s is equals to 0 in this expression, this term becomes 1 and this integral can be equated to that one. So this implies if I need to evaluate 0 to infinity e to the power minus of 2t minus of 6t by t dt, then this can be taken as Laplace of the same function e to the power minus 2t e to the power minus of 6t by t. But what I have to do? I have to replace s with 0 in it in order to evaluate these integrals. So now instead of evaluating this integral, what I do? I evaluate Laplace of this function and finally I will be replacing s with 0. So now we evaluate Laplace of e to the power minus of 2t minus e to the power minus of 6t. We have to use two properties here. First, Laplace of elementary functions and then Laplace for division by t. So now again, we first apply linearity property. That gives me Laplace of e to the power minus 2t, then Laplace of e to the power minus of 6t. So this gives me again 1 upon s plus 2 and 1 upon s plus 6. So we have obtained the Laplace of exponential. Now we will be using the property for division. To apply the property for division, I write down Laplace of e to the power minus 2t minus e to the power minus of 6t by t. The property of division was if I have Laplace of ft by t, then this can be written as integral s to infinity capital F of u and du, where this capital F is Laplace of this ft. So now I write down it as integral s to infinity, then the Laplace was 1 by s plus 2 minus 1 by s plus 6 and ds. Again, integrating it, I get the result as log of s plus 2 minus log of s plus 6, and the limits are s to infinity. This term can be again written as log of s plus 2 by s plus 6, limits s to infinity. Now since the limits are from s to infinity, so I have to adjust the function s in the form of 1 by s, otherwise infinity cannot be replaced. So I write down this function as log of 1 plus 2 by s and then again 1 plus 6 by s. And now I have to replace limit s to infinity. When I put the limit infinity in this, this becomes 2 by infinity 0, 6 by infinity 0, and I get the result as log of 1, which is 0, and the next term becomes log of 1 plus 2 by s, and I have 1 plus 6 by s. Log 1 is 0, so I am left with only this quantity, and since I have a minus sign here, I can reciprocate the function and it becomes numerator in the denominator and denominator in the numerator. So the result becomes log of s plus 6 by s plus 2. So this is how we have calculated the Laplace of this function. Now what we have to evaluate? So further we have to evaluate I have to evaluate this integral 0 to infinity e to the power minus 2t minus e to the power minus of 6t by t and dt. And this we have already explained that it was equal to Laplace of e to the power minus of 2t minus e to the power minus of 6t by t, and I have to replace s with 0 in this. So again I have calculated the Laplace, I replace it here, log of s plus 6 by s plus 2, and I have to replace s by 0 here. So when I put s as 0, this gives me log of 6 by 2, or I get the result as log of 3. So this is our evaluation of the integral. So you can evaluate any definite integral by means of calculating its Laplace transform and then replacing the value of s accordingly. Let's take one more example. Now again I have to evaluate this integral. The limits are 0 to infinity, that was our necessary condition. After that I have e to the power minus 2t in the kernel. So again it can be solved by Laplace. So now we consider integral 0 to infinity e to the power minus st. Since I have exponential, I need not introduce a new one, sine square t by t and dt. So this is definitely Laplace of sine square t by t. Now again, instead of calculating this integral, what I have, so therefore I can write down integral 0 to infinity e to the power minus 2t sine square t by t dt. You can compare these two. They are entirely same, only difference is s replaced with 2 here. So I can write down Laplace of sine square t by t with s replaced by 2 in this expression. To remember this equation, you can number it as 1. Now what I need Laplace of this complete function. So now I proceed as finding the Laplace of sine square t. Now to find out the Laplace of this sine square t, I need to write it as the form of 2 theta. So 2 theta mein sine square t can be written as 1 minus cos 2t by 2. So I write Laplace of 1 minus cos 2t by 2. We can apply linearity property to it. That gives us 1 by 2, then Laplace of 1 minus Laplace of cos 2t. These are again your elementary functions or standard functions. So 1 by 2 as it is, Laplace of 1 is 1 by s, and Laplace of cos 2t is s upon s square plus 4. So we have first calculated the Laplace of sine square t. Now since it is divided by t, so as in the previous question, I have to again apply the property for division by t, and then this Laplace will be converted to an integral. So we now write down Laplace of sine square t by t. This will be 1 by 2 as it is, then I have integral s to infinity 1 by s minus s upon s square plus 4 and ds. Integration of this function gives us 1 by 2 as it is, 1 by s will be converted to log s, and s upon s square plus 4 will be converted to 1 by 2 log of s square plus 4. The limits s to infinity. Again, log can be combined together. So I can write it as 1 by 2 log of s upon s square plus 4 to the power 1 by 2, and the limits of integral will be s to infinity. Now again, since I have the limit infinity, so s has to be adjusted in the form of 1 by s. 1 by s में adjust करने के लिए I write down the result as 1 by 2 as it is. Then I have to divide the numerator and denominator by s. So I get log of 1 upon 1 plus 4 by s square to the power 1 by 2 and limit s to infinity. Now I put the limit infinity. So when I put the limit infinity, I'll be getting 1 by 2. Then at infinity, 4 by infinity is 0, and I will be getting log of 1 again. Remember this thing, whenever you are having the limits infinity, you have to adjust the function so that there is no s, there should be only 1 by s. Now when I put the limit s in this, the function remains same, and I have log of 1 upon 1 plus 4 by s square to the power 1 by 2. After that, log 1 is 0, minus can be taken inside, and the function u by v can be written as v by u. So we get 1 by 2 log of s square plus 4 to the power 1 by 2, and power 1 by 2 again can be taken out. So I can write 1 by 4 log of s square plus 4. So this is our Laplace transform of sine square t by t. Now by equation 1, which we have discussed earlier, so by equation 1, what I need to calculate? I need integral 0 to infinity e to the power minus 2t sine square t by t dt, and that was equal to Laplace of sine square t by t, and I have to replace s with 2 in it, right? So now this gives me, I have already calculated Laplace, so I write down 1 by 4, then I have log of s square plus 4, and this was s square also. This s square should be there. So this is s square plus 4 by s square. So further, I put s is equals to 2 in it. So when I put s is equals to 2 in it, I get the result as 1 by 4. This becomes 4 plus 4, 8 by 4. So I get 1 by 4 log of 2. So the result is 1 by 4 log 2, that is the value of this integral. So again here we have used the transform of elementary functions and then division by t property to evaluate this integral, where we have finally replaced s with 2. Taking one more example, we have to evaluate this integral. Again, I write it as the Laplace of a new function. So again, I consider integral 0 to infinity. Since I have this integral from 0 to infinity and one exponential is also there, so we replace this exponential with e to the power minus of st multiplied by t cos of 2t and dt. So this is Laplace of t cos of 2t, right? Now further we compare the given integral. So this implies integral 0 to infinity e to the power minus of 3t multiplied with t cos of 2t and dt. Now you can compare these two. They are entirely same with s replaced by 3. So I get Laplace of t cos of 2t with s replaced by 3. So this can be our first equation. Now I need to calculate Laplace of t cos 2t. So again we have to use two properties. Firstly, I'll calculate Laplace of cos 2t, and then I will apply the multiplication of t property in order to calculate Laplace of t cos 2t. So now we find out Laplace of cos 2t. This is your elementary function, and its Laplace is s upon s square plus 4. The next term is Laplace of t cos 2t. Multiplication by t property. So we can write minus of d by ds s upon s square plus 4. This gives us minus as it is. I have s square plus 4 whole square. Then I have s square plus 4. Then I have minus of 2s square, which on simplification gives us s square minus 4 upon s square plus 4 whole square. So this is Laplace of t cos 2t. Now you can compare these two equations together, and so by 1 and 2 I can find out the value of this integral 0 to infinity e to the power minus 3t t cos of 2t and dt. This is equals to Laplace of t cos of 2t, where I have to replace s by 3. So I get s square minus 4 upon s square plus 4 whole square with s replaced by 3. So that gives us 9 minus 4, I have 5, then 9 plus 4, 13 square is 169. So we have evaluated again this definite integral. So the thing to remember is any definite integral which varies from 0 to infinity and has exponential in its kernel or integrand can be evaluated by means of Laplace transform. So this is all for this class. In this class we have learnt about convolution theorem and how to apply it to find out inverse Laplace transform, as well as we have discussed how to evaluate certain definite integrals by means of Laplace transform. So again, what you have to remember after this lecture, you have to remember that inverse of the product of fs and gs can be calculated by f of u g of t minus u from 0 to t integral, and this is again denoted as f star g or convolution of f and g. So this is all for today, and in our next lecture we will be discussing how to solve ordinary differential equations with Laplace transform, which is again the most important application of Laplace transform utilized in your many other subjects as well. So thank you.